Okay, let's talk a little bit about geology. This is one of my favorite quotes. I begin about every class with this, so some of my students that are here probably have seen this one before, and this sums up geology pretty nicely. Okay, I'll read it to you. On first examining a new district, nothing can appear more hopeless than the chaos of rocks. Anybody take an introductory geology course before and have all those boxes out in front of you? And how am I going to tell these things apart? Nothing can appear more hopeless than the chaos of rocks. But by recording the stratification or nature of rocks, that means describing them, looking at them in cores, looking at them in outcrops, making a map of what rocks are where, and looking at the fossils that ties together the ages of the rocks, always reasoning and predicting. There's the science there. What will be found elsewhere, light soon begins to dawn on the new district, and the structure of the whole becomes more or less intelligible. So what's that really mean? What do we do as geologists? Look at rocks. Yes, that's what we do. And we all know through some of the lectures that you had earlier today that if you look around us here, everything around us here came out of the ground, one way or another. Either it was grown or it was mined. Okay, if you look from the fabric of the carpet to the metal that makes up the tables to the cotton that's the fabric for some of these things, it all was grown or mined. So there's been a hand of a geologist that has helped us lift up society into the infrastructure that we have today. So what's underneath our feet is the first level of scientific infrastructure and societal infrastructure. So what do we do? Look at rocks? The short answer to that is yes. So what do we really do? Geologists are the science that's tasked with figuring out what the earth is made of and how it works. Well, haven't we done that already? Well, yeah, we've had geologists boots on the ground just about everywhere, and from the Antarctica to northern Canada, all the way across the world to the highest mountains, but we still don't have a good scientific understanding of a whole lot of it. So one of the things that I do at Illinois State is, I forgot to introduce myself, didn't I?
Somewhat.
Okay. I'm Malone. I'm a professor at Illinois State. I've been there for the last 25 years. I specialize in structural geology, that's folds and faults, and I specialize in sedimentary geology. I teach courses in field geology. I just got back from the Wyoming field camp. I teach spring break courses to West Texas and New Mexico. I teach a course in layered rocks in space and time called stratigraphy. I teach a course in structural geology, and I teach a course in petroleum geology of Illinois, and I rotate through those on a yearly basis. I also do the academic advisement for our geology majors. So I'm responsible for making sure that they take the right classes in the right orders and graduate on time with as little debt as possible. And I also do research. I have a lot of fun research projects going on that I can talk to you about sometime, but one of the more exciting things, I guess, if you're a geologist, is I've been working with some of the folks from Illinois State Geological Survey, and we found some Cambrian-aged rocks deeper in the Illinois Basin than anybody that thought there was Cambrian before. And we have some of the evidence for the earliest history of the Illinois Basin that we can talk about a little bit if you like. But this is more general. So what do we need to know to be geologists? We got geologic reasoning. How do geologists think about stuff that other people don't? So you're going to hear us talk about Ordovician and Pennsylvania, and those are just kind of words. We'll throw around, well, the Jurassic was 150 million years ago. The Cambrian started at 540 million years ago. What's that mean? Okay, hundreds of millions of years. We throw those around like they're paper clips. And we have to be able to think in terms of deep time. Remember, the human life, if you're lucky, is somewhere around 100 years and probably a little less than that for most of us. And when we start thinking about the vast expanse of geologic time, you know, our minds start to gray over and we wonder what that really means. So we have to think about the concepts in the deepness of time. Another thing that we have to think about when we do geologic reasoning is the only thing that's constant is change. And many of you have lived near where you grew up, and you've lived there for a long time, and when you grew up, you remember the world looking like the way that it did. Then you see, oh, there's some development that comes in, or a new building that's getting put up, or it's been reclaimed, and you think about the changes that happen in a human lifespan. Well, changes happen geologically too. So if we think about the Illinois Basin area, most of the Paleozoic, 250 million years of it was spent underwater. We were in an ocean, a shallow sea, similar to what we'd find in the Florida Keys. If we look deeper back in geologic time, say about 1.5 billion years ago, we had mountain building going on in Illinois. The problem is all that evidence is buried by younger rocks. So the only thing that's constant is change. The Earth is an entity that is constantly evolving. Okay, it's constantly changing. So one of the things that I like to put into perspective is that, yeah, we've increased CO2 concentrations in the atmosphere, possibly, likely because of burning of fossil fuels, and we're at about, what, 470, 480 ppm CO2 in the atmosphere now. Well, if we think about the Ordovician, the late Ordovician in particular, 460 million years ago, global CO2 was about 2,000 parts per million. The average ocean water temperatures were 90 or 100 degrees Fahrenheit, and there was glaciation occurring at high latitudes. So we have to put into perspective the things that occur naturally. And we also, another thing that I'd like to point out too is, did you know 2.4 billion years ago the Earth began to be poisoned with oxygen? Oxygen was a horrible poison when it was first advented through photosynthesis about 2.4 billion years ago. Half of geologic time had no oxygen. Couldn't support multicellular animal life as we think of it today. Yet those crusty cyanobacteria doing what they do, photosynthesizing, pumped out all this oxygen into the atmosphere and poisoned off all of the sulfur-reducing bacteria that was around at the time. They pretty much occupied every available niche, and they got in the way of everything. They even blotted out the sun. There were so many of them, so they couldn't photosynthesize anymore. So that is a tongue-in-cheek way to illustrate a point that change is everywhere, change is constantly happening, change is natural. And there's a tremendous amount of feedback between the living and non-living world. So because there was oxygen in the atmosphere, that allowed us to get all the iron out of the system. It allowed us to put iron in sedimentary rocks and leave those behind for us to be able to mine for the iron that we need for an industrialized society. Most of the time this change is gradual, but sometimes it's catastrophic. Okay, so what do? What do geologists really do? We observe rocks directly, and that was the essence of the course that I just got done teaching. This was year 28 teaching field geology to a total of 798 students now. At the rate I'm burning through students, I got 7 more years before I can retire to hit that 1,000. So that's my goal. If I can get to that, I think I've done something important. So we observe rocks directly. Geologists are all the time looking at rocks, either in the field themselves or what comes out of the ground. I think all the geologists here that are presenters have looked at miles and miles of rock core that came out of the ground. That's the straw that we stick in to figure out what's in there, and it's something that we do. So we use outcrops and we use drill core. We make a lot of maps. You've seen a lot of maps. You've seen a lot of cross sections. So geology is a very visual science. We try to understand what the earth beneath our feet looks like in 3 dimensions. And in doing that, we can figure out, well, maybe where's the oil, or where's the gold, or where's the copper, or where's whatever we're looking for. So we also look at things indirectly through geophysical observations, and we really torture rocks. Okay, we can pass all sorts of sound waves through them. We can pass all sorts of electrical currents through them. We can check their magnetic properties. We can see how heavy they are. When we get them back to the lab, we pour acid on them to figure out what's in there. We cut them into little thin sheets. We put all sorts of lasers on them to figure out their most appalling secrets. So we use a lot of indirect measurements, what we call geophysics too. We determine ages, and sometimes that age is simple. The oldest is at the bottom of the pile, the youngest is at the top, but sometimes that can get a little bit more interesting. So in geology, we have to have this chronology. We have a time scale, okay, and those words like Ordovician and Pennsylvanian mean something to us. We figure out all the physical, chemical, and biological properties. Hey, the best way to do chemistry is with the granite. It's not all those stinky things that you can make inside the test tubes or make things go boom and make strange noises. We can actually look at chemical reactions with the crystal structures that we have within rocks. Then once we've made all these observations, we try saying, well, maybe the Devonian rocks in Illinois kind of look like the Devonian rocks in Michigan or Texas, so we can have a broader understanding or synthesis. Okay, so I like to think of what we do is reading the book of rocks. So if we think of the geology of Illinois and many other places, we have strata or layers, and each of those layers tells a different story. You can think of those layers as a different page in a book. And one thing to keep in mind is that our deep earth history has no first-hand accounts. Nobody was there to take down this history or to record it and to pass it on. So geology is the science that records recovers this lost memory. So we abide by the scientific method, we test hypotheses, we formulate hypotheses, we test hypotheses, we do all sorts of measurements and experiments on these rocks to try to figure this out. So we recover the lost memory of the history of the Earth. And that history of the Earth is important to try to figure out where the oil is or where the oil isn't. So this is all part of the game. So reading the rocks is messy. There's a lot of uncertainty that comes with making these observations. You can make the same observation on two different sets of rocks, but that doesn't necessarily mean they formed in exactly the same way at the same time. You can maybe come close to that, but it's not certain. So I always look at this as a 1,000-page book written in several languages with most of the characters missing that's always being revised. So you can maybe tell you something. Think about that 1,000-piece puzzle, the jigsaw puzzle that you'd use. If you get one key piece of that puzzle, you might be able to say something, hey, I think that's sky, or I think that's water, or that's the tail of a squirrel, or something in that picture. You might be able to have one clue that's really good, but the other ones, maybe not so much until you start piecing them together. So every texture of a rock, how coarse it is, how fine is it, what's its porosity, every mineral that's in there, every structure that's in there, every fossil that's in there is a clue for understanding what it was like in the geologic past. So I like to think of geology as a forensic science. It's a crime scene. We go and look at what happened and we try to reconstruct what happened. So that's what forensics is all about. So ultimately we're trying to understand what the Earth is made of, how it works, and its history for the last 4.5 billion years. Heck, that's no small task, is it? So we probably all know this theoretical background. And Otis Redding probably said it as well as anybody in the Shawshank Redemption. Geology is the study of pressure and time. That's all it really takes, pressure and time. Do you remember the next sentence? That and the big GD poster. So this is the Shawshank Redemption. So sometimes geology isn't so gradual and isn't so subtle, but very few things impact the entire world at the same time instantaneously. So one of the things that we use in the study of geology is the concept of uniformitarianism. And what that means is the present is the key to the past. So if I went and observed what happened at Mount St. Helens on May 18th, 1980, and I happen to find some 50-million-year-old rocks that have similar textures and structures, I would then be able to interpret that, hey, maybe something like what happened at Mount St. Helens that we did see also happened in Wyoming 50 million years ago. So that's how we would use uniformitarianism. So that there are oceans today that have waves that deposit these types of sediments, we would also assume that if I saw these types of sediments in the past, then maybe I had a similar kind of ocean at that time in that place. So that's uniformitarianism. The present is the key to the past. And when we study sedimentary rocks in particular, we abide by what we call Steno's principles. And there are three aspects of sedimentary rocks which we can rely on pretty well. So this is an outcrop of the Boquillas Formation, Cretaceous in age. It's about 100 million years old, and it's in the Big Bend region of West Texas. It's at, by Boquillas Canyon. And if we look there, what stands out, I think, most obviously here is that the rock is in layers. Each one of these individual layers formed under a certain set of conditions. These happen to be limestones that are marine. So the ocean was a particular salinity. The ocean was a particular depth. It had a particular amount of light, and anything else that you can think of with respect to that piece of ocean, it's going to yield this kind of sediment. And then we have kind of two different types of sediment that are evidenced by how the color is and how thick the layer is. So maybe we alternated between a couple of conditions. Maybe sea level was going up and down a little bit. So maybe when it got a little bit higher, these limestones couldn't be deposited. So we also think in terms of when this is the same Boquillas Formation a few miles away, these same layers are crumpled up here. So we would think that something happened later on in the history of these rocks because they're no longer the shapes and sizes that they are now, so maybe something happened later to impact these. So Steno's principles are superposition. That means the oldest is at the bottom. Think about your laundry basket. If you do your laundry once a week and that laundry is done on Saturday, the Sunday clothes are the ones at the bottom of the pile. Those came off first, and the Friday clothes are the ones at the top of the pile. So that's superposition. The oldest is at the bottom. Another thing that we have here is the continuity of beds or the continuity of strata. Each of these individual layers are thin with respect to their lateral extent. and that reflects the nature of the environments of deposition. And finally, sedimentary layers are laid down on a flat or close to flat surface. So when we see something like this, and this is in a small version of an anticline, these are important in oil traps here, especially in the Illinois Basin, we can try to understand the processes of deformation of these rocks after the sedimentary aspect of their history is concluded. So another thing about geology and majoring it, it's the best major around, because I remember back when I was going to school, when I took the aptitude test, I actually listened to them. So when I was back in junior high, do you still give the aptitude test to the kids? They don't do those anymore, where it says what you're supposed to do when you grow up based on how you answer the questions. I was told I should be a physicist or a geologist. And I got to thinking about it. Well, physicists get to work 50 weeks a year to spend 2 weeks in the mountains, and heck, the geologists get paid to go there to begin with. So that was an easy choice for me to be the geologist. But we get to go to glorious places and do field work. And this is one of the research areas I have in the Bighorn Mountains of Wyoming. I've also had the opportunity to do some field work in Alaska. And let me tell you, walking to the top of the hill is nowhere near as fun as getting the elevator to the top of the hill. And this was this was actually copper exploration down on the Alaska Peninsula about 10 years ago. And this is some more of that. So this is the morning briefing. This is what geologists get to do. And what a lot of us get to do is spend a lot of time outside looking at rocks. So if you have students that are interested in doing those types of things, this is something that you should recommend to them. You know, there are mosquitoes. That's the state bird in Alaska, so you got to be careful about that. But this is this year's field camp. We have students from, we had 30 students at field camp this year. We had 5 different countries represented. I had some Saudis, some Angolans, a Pakistani, a Lithuanian, and a Nigerian intermixed with the Illinois State University students. So each of these field camp groups kind of look alike. We, of course, are safe, and yes, they're taking their notes, and we have the beautiful Absarica Mountains as a backdrop. And these are some of the kinds of things that we do at field camp. We learn how to describe rocks, observed rocks, and measure their orientations, and this helps with becoming the professional geologist later. I still got 2 minutes. Okay, so what I have here, and I'm sorry if somebody talked about this one already, but this is important for the next part of the talk in training geologists, is that inflation-adjusted prices. So really the discipline of geology rises and falls. How many students we have enrolled in geology programs depends on commodities prices. When commodity prices are high, we have more majors than we know what to do with. When commodity prices are low, we're scrounging around wondering whether the dean's going to cancel us or not. So if we look at inflation-adjusted crude oil prices over time, this is through March 2015, all the way back from the end of World War II, we can see that oil is valuable in the most valuable compared to inflation-adjusted dollars back in the late 1970s and in June 2008. So guess when we had the most geology majors being cranked out? In the late 1970s. When oil prices fell through the floor, geology programs suffered enrollments. And we had this rise in oil prices, and when we're here at the IPRB 5 years ago, we were probably thinking it's going to stay up there for a long time. That wasn't a very good guess, and it came back down, and we've been hovering around this $50-ish a barrel for the last few years. So part of this is economic, part of it is geologists get better at what they do. So we're kind of our own worst enemies sometimes. If we have high prices, we come up with a whole bunch of good ideas and technology to get more oil out of the ground. And then we kind of price ourselves out of the market a little bit until the demand gets higher again. So, it's hard to predict what the future has in store. We're always going to be using oil. Whether we're always burning it or not, I'm not sure. But we're always going to be needing it for a wide variety of things. And I think that the future is still bright for geology majors. And I'll brag up my own program. We turn more than 90% of our geology majors into geologists. And we also place them in a wide variety of different things. We're focusing on extraction here, but there's environmental jobs, there's government jobs, there's all sorts of other things that our students can do. And that's probably a good place to stop.